Good morning. Today we're going to talk about work in three dimensions and we're going to talk about power. When I say work in three dimensions, I mean how do you use a force which is a vector and perhaps a displacement that is a vector and calculated work which is a scalar. Well, since the force and the displacement are vectors, the way that we define work for a vector force exerted over a vector displacement is as the dot product of the two. Remember, there's two different definitions of the dot product, and one of them matches perfectly our definition for work. We know that only the component of the force that acts in the direction of the displacement does any work. So this is where we get this definition of work as force cosine of theta times the displacement in the x direction. F cosine theta, where theta is the angle between the displacement and the force, gives us this equation. Another way you could say that it is the x displacement times the x component of the force that gives us the work done by the x component of the force. But you could also say the same thing about the y and the z components. If there is a force in the y direction, and that force times the y displacement should give us the contribution of the y force to the work, and similarly the z force times the z displacement should give us the contribution to the work from the z component of the force. And so ultimately then, the total work being done is fx times delta x, fy times delta y, and fz times delta z, all added together, and that's just the dot product. So the work is equal to the force dotted with the displacement vector. Now what if your path is curving and it isn't just a straight line like that, like your vector doesn't keep the same direction? Well, we won't actually do that kind of thing in this class in a quantitative way, because in order to do that, you have to know a little bit about vector calculus or multi-variable calculus. We will just do it conceptually. We'll do it in simple situations where it's easy to figure out what the force is over a displacement, even if that displacement curves, as long as it curves in some simple way that we can characterize like a circle. But if we were to do this in a more formal way, we would just take our displacement and take a very small segment of our displacement, just like we talked about when you were talking about calculating work as the area under the curve. You take the force times the small segment of the displacement in the x direction. Well, here we'll just take a small displacement along the curve, and we'll dot that with whatever the force is right there. And then instead of adding them up, we're going to integrate, that is to say, add them up over small little pieces, and that's how we find the total work that's done. Well, we can sometimes solve these without having to do any kind of vector calculus. For example, what is the work done by the force of gravity of the Earth on the moon during a lunar month? A lunar month here is going to be defined as the time it takes for the moon to go around the Earth one time. And we're also going to assume that the moon is moving in a circular orbit and that's moving at a constant speed. Well, you can see that anywhere in the orbit, the moon is going to be, the force on the moon is going to be towards the Earth. And therefore, since it's moving in a circular path and the Earth is at the center of that circle, the force is always perpendicular to the displacement of the moon at any given time. So no work is done. Lastly, let's talk about power. Power is the rate at which work is done or energy is transferred. We need to keep the definition a little bit more general. For right now in mechanics, we'll usually look at it as the rate at which work is done let us say energy is transferred via work. When we deal with electricity, we'll see that it's also the rate at which energy can be transferred by a charge moving through a circuit. So power is just equal to the change in the amount of work that's done. Delta W here means the amount of work that's done from one initial state to the final state, divided by the time. Now, there's another way to say this too. Think about work as being the component of the force in the direction of the displacement times that displacement. So work is equal to Fx delta x, which means the power should be Fx delta x divided by delta t. What's delta x over delta t? Well, that's the average velocity, and if you do it over a very small time interval, it's the instantaneous velocity. So the instantaneous power, the power at one instant in time, is given by the force times the velocity. Let's do an example. A motor is used to lift up a load of lumber weighing 400 newtons to a height of 5 meters in 10 seconds. What is the minimum power the motor must produce? Calculate it two ways. Well, let's calculate it by calculating the total work that's done first, and then we'll divide that by the time. 400 newtons is the weight of the lumber, and we are to lift it at the minimum amount of power, which means we're going to lift it at a constant speed. Clearly, to get it moving, you'll have to apply a little bit more force than its weight, and then at the end of its motion, to stop it from moving, you need to apply a little less force than its weight. But over most of the motion, the amount of force the motor is going to have to apply is equal to the weight of the load of lumber, which would be 400 newtons. And now, if that was applied over a height of 5 meters, that is 2,000 joules. And that 2,000 joules is being, that much work is being done on the lumber in 10 seconds. So 2,000 divided by 10 is 200 watts would be the minimum power. Now, what's the other way to do it? Well, it's going 5 meters in 10 seconds. That's 0.5 meters per second. So the force of 400 newtons times 0.5 meters per second gives me force times velocity. That gives me 200 watts. So doing it either way gets you the same result. In 3 dimensions, we would just have to expand our force vector and velocity vector to take into account all 3 ways that the forces could apply the force could be multiplied by the velocity in all 3 directions and then added together. Let's do a couple of practice questions here. An object is initially at rest. A net force, which always points in the same direction, is applied to the object so that the power of the net force is constant. As the object gains speed, well, the power is supposed to stay constant. So go ahead and stop the video for a second and then see if you can state the answer. You know that the force can't stay constant because the speed is getting bigger, and force times velocity should give us the magnitude of the power. So if the power is to remain constant, the force must decrease when the velocity increases.